Well, hello. So this is going to be a pretty short lecture. I don't want you to spend a lot of time watching more videos yet, but just a extra session just to give you more practice with Lewis structures. And so this is one that we didn't look at any examples on Tuesday of structure with a positive charge. And so this is how you would handle um, hydronium ions. So H3O plus is known as the hydronium cation because it's positive charge. Okay, and so for this, you will add up all the valence electrons. You've got 6 for oxygen, 7, 8, 9, and then you take away 1 because you've got a plus charge. Okay, so 8 valence electrons total, and you follow the same thing here. Okay, so you've got, each of the hydrogens are bonded to the central oxygen. So I guess kind of to show you in steps here. Okay, so we're going to place 8 valence electrons. So we place, okay, so we place 6 and then 7, 8. Okay, and you typically will do this somehow to indicate its positive charge. The positive charge in this case is really at the oxygen, right? So the formal charge is 6 minus 3 bonds minus 2 dots. Okay, so that's plus 1. Okay. This one is kind of interesting. So this is a organic compound. And so in this case, again, it's the atom on the left of the structure, or this formula, that is the central atom. And so carbon is in the middle. Okay, so we're going to place 12 valence electrons around this. And so we're going to have, in this case, an oxygen and 2 hydrogens. Okay, and so now that's 6. Now you go around the outside for anything that can take more electrons. So hydrogens are already happy with 2. Okay, so we don't have to do anything there. Those are smiley faces. I don't want to get those confused with dots here, so let me let me get rid of those. Okay, so we've placed now 6 electrons. So to get to 12, we do 7, 8, 9, 10, 11, 12. Okay, around the outside. All right, and now you look for, is everything happy as far as the octet rule? And you see that carbon has less, and so we have to use double bonding. So that's where that double bond comes from. Okay. All right. SF6 is an example where sulfur can have more than 8 electrons. And so if you look at sulfur here, you've got 6 bonds. So this is actually surrounded by 12 electrons. But again, it's happy. Okay, it can expand its octet. There are a few reasons why some textbooks describe why it's possible. A lot of textbooks will say because sulfur, if I go back here, because sulfur is closer to the transition metal series, that you can put electrons into the D, the 3D orbital, and so that's why it can accept, more than 8 electrons. It sounds good, but that's really not correct. The D electrons are too high in energy to be used in bonding, and so there are other explanations related to, why can sulfur, phosphorus, or these ones, and all these below, why they can expand their octets. And we won't go into those reasons here. I guess if you're curious, let me know, and I can do a hand waving explanation. You really have to know more about bonding theories to get into that. But for this class, just I guess know that any element in the third period and below can have more than 8. Okay. Iodine is another one that it's far down in the halogen series, so it can have more than 8. Here you've got, what is it, 6, 7, 8. So you've got 10 electrons around the iodine. Okay, and it's totally happy. Ozone is another type of resonance form. Okay, and so you've got 18 electrons. If you draw it, and then your next step would be to put all the dots around everything. So you build up around the outside, and then you still have 2 left over. Okay, so to kind of show you that in steps, so we would be like this. So that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. Then you look at the oxygen. The central oxygen isn't an octet, so you can do, one of these numbers, okay? But you could have also done that from the other side. Okay, and so this is why ozone actually has a resonance structure. Okay, so the true Lewis structure for ozone is kind of like this, right? Where you've got, again, oxygen-oxygen bonds, which are kind of like a bond order of 1.5. Okay, it's between a single and a double bond. Okay, so it's kind of between those two. All right. The notes, the PowerPoint gives a different formula for formal charges. It's okay to do it this way as well, where you're taking half of the number of bonding electrons, and it's the same except this really. You can use this formula. I think it's, I don't know, maybe more complex because you've got a half here. Again, the formula I have always used is just the number of valence minus the number of bonds emanating from that atom minus the number of individual electrons. Okay, just count up the dots, not as pairs, but individual dots around it. Okay. All right, so when we get back to regular lectures, we'll talk about shapes of molecules. I just want to take just a few more minutes and look at some different examples for Lewis structures. And so here's one. What about this? So nitrous oxide. Okay. And so if you look at the number of valence electrons, you will have, so 10 from the nitrogens and then another 6. So you've got 16 valence electrons. Okay, so that's how you would put these together. I guess if there's any ambiguity, I will tell you, in this case, I have in the past put this on an exam as an exam question. And so I would tell you that the atom order is this. Okay, so again, I'll make that clear on exams. Okay, so we have to place 16 electrons. And so we've placed 4, so let's build up around the outside. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so now we look at, nitrogen and oxygen both have to have an octet. And so we could do, let's say, this one going to there. Okay. Or we're still not so, each of the, that one has an octet, that one, but the middle nitrogen still doesn't, right? So our only other kind of strategy here would be to promote those electrons. Okay. And so now, if we look at everything as far as having an octet, each of the nitrogens are surrounded by 8 electrons and the oxygen. Okay, so everything satisfies the octet rule. Okay. If we look at formal charges, the formal charge of this nitrogen is its valence electrons minus 2 bonds minus 1, 2, 3, 4 dots. So that's a minus 1. The formal charge on this one is 5 minus 4 bonds. So that's a plus 1. And then that oxygen is 6 minus 2 bonds and 4 dots. So that's a 0. Okay, and so again, our rule says that if at maximum you can have either a plus or minus 1 as formal charges. So that's cool. Okay, so this would be a good possibility. Okay, so this would be the best Lewis structure. Getting back to dinitrogen, or just the nitrogen molecule, again, so it says 10 valence electrons. The reason why it has to be triply bonded is you would do this too, right? So you start with that, so it's 2 electrons, 3, 4, 5, 6, 7, 8, 9, 10, let's say. Okay, so then you're looking, and this nitrogen doesn't have an octet, so you can do this. It still doesn't. Now it does. Okay, so that's why that is the best Lewis structure for nitrogen and oxygen, with 12 valence electrons. You've got 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so again, okay, that oxygen doesn't have an octet, so we can do that number. And now, whoops, I'm just trying to erase his unhappy face here. Well, okay, it's not working, but he just wants to be unhappy today. There we go. Okay, so now everything is happy as far as the octet rule for both of the oxygens. Okay. Let's look at a lot of the, here's kind of a trick or hint. Most resonance structures will be, if you have like NOx with charges, they may or may not have charges, but if you have NOx, SOX, a lot of ClO whatevers, phosphorus. Okay, so a lot of these atoms bonded to oxygens, chances are they will have resonance structures. Also carbon, right? We already saw. Carbonate, for instance. So CO3 2 minus, I guess, is really the only one, but also carbon with oxygen has resonance. Okay, so those are kind of ones that if you see on an exam, like this, for instance, whoops, that, okay, already start thinking, it probably has resonance. Same with this one. Nitrate, nitrite, okay, those will all have resonance forms, okay. If we look at nitrate, let's look at NO3 minus, okay. So to draw the Lewis structure for that one, we have 6 times 3 for the oxygens. And then nitrogen is 5. And then the minus charge, we have to add in another 1. So that's 24 valence electrons. So we place 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, and then you look, and the nitrogen doesn't have an octet, but it needs one, so that's when you do this. Okay, but you could have done it, up here, or what's the other one? I guess here. Okay, with all these other dots around here. Okay, just being lazy. Okay, whoops, up here too. Okay, so this would have 3 resonance forms or resonance structures. All right. Now, what would you do if, and there are exceptions, and the only one that you'll actually see in practice, and it's an easy one to remember, it's in your face as no. Okay, so it's like somebody, because it's in capitals too, it's like screaming no at you. Okay, this is nitric oxide. Okay, and NO2 is another one that we're going to talk about in a second. Okay, so this one is an exception to what we've been talking about as far as, nitrogen and oxygen absolutely have to have an octet because you'll have an odd number of electrons here. And so why this is so reactive is because if you add these up, you'll have how many valence electrons? You've got 6 and 5, so we have 11 valence electrons. Okay, so an odd number. And so if we start to place it around here, there's really 2 possibilities for this. So we could say, you got 2, and then start building up around the oxygen first. 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, or maybe, if you're a lefty, for instance, then you build up around nitrogen first. So it's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so those are the 2 possibilities for nitric oxide, or nitrogen monoxide is another name. Okay, and so how do you determine then which one of these is correct? Look at formal charges. Okay, and so in this case, the oxygen, the formal charge is going to be 6 minus 1, and then you've got 1, 2, 3, 4, 6 dots. So you're going to have a minus 1 formal charge. This nitrogen is going to be 5 minus 1 minus 3, so that's a plus 1. Okay. In this case, the oxygen here is going to be 6 minus 1 bond, and then you've got 1, 2, 3 dots. So that's a plus 2. This nitrogen here is going to be 5 minus 1, and then 1, 2, 3, 4, 5, 6. So that's a minus 2. Okay, so you can see that, those formal charges are never going to be possible. Okay, so a person could then say, well, instead of it being this, then why not do a double bond? Okay, so to say that instead. Okay, and so now if you do the formal charges, then it will be 5 minus 2 bonds, 3, or 1, 2, 3, 4. Okay, so that's a minus 1. And then this oxygen is going to be 6 minus 2, and then 3, so that's going to be a plus 1. Okay. And so looking at these 2 possibilities, okay, so this is kind of the more realistic one, I guess, versus this is just not going to happen because formal charges are too high. Okay, so you've got this where you've got like a dot on the oxygen. Or if we go back to that first one, if I redraw that, what was it? We've got all the dots here, like that. Okay. And then we had a minus charge and a plus charge there. Okay. Which do you think would be more preferable? Okay. Having a plus charge on the oxygen or the minus charge on the oxygen? Okay, and I guess this is recorded, so you can't speak back to me, so I guess I shouldn't wait too long for your answers. If I go back to the periodic table, which is more electronegative, oxygen or nitrogen? And you'll see that oxygen is more electronegative than nitrogen. Okay, so then the structure that has the formal charge of -1 on the oxygen is going to be preferred. Okay. So that's really getting into detailed, analysis of which is the best Lewis structure or not. But one time the ACS had that as an exam question. I might follow suit now that I've told you about it, and put one like this on the exam as well. Okay, so if there are different possibilities for a Lewis structure, look always, I guess, here are my steps. Okay, so the first thing is the octet rule. Okay, and then look at exceptions. Okay. Okay, if they're possible, so if you can have something with more or less, okay. If there are, no exceptions, so for instance, carbon or nitrogen that have to have 8, then you start to use, use multiple bonds. If an atom needs 8 electrons. Okay, and then as a final check, look at formal charges. Okay, and then they should again be either 0 for everything or at the most plus or minus 1. Okay, and then as a final check, let's say you do have charges that are plus and minus 1. Is the minus charge on the most, or charges on the most electronegative atom or atoms? Okay. And so those are really the 4 things to look at to determine whether you have the quote-unquote best Lewis structure. Okay. All right, and most of the time, this last part will be pretty evident. Like remember, for sulfate, where we had this one, we needed the double bonds, to get formal charge of the central sulfur to 0. And then you had the minus charges appeared on the oxygen. So often, most of the time, they'll automatically work out where the negative charge will be on the most electronegative atom. It's just really, you will get some like NO, for instance, those ones, where they're pretty close in electronegativity, and you have, a couple possibilities for it. Okay. By the way, this structure, so the real one, if I draw it clean here, okay, so this again is the best structure. This is called a radical, sometimes called a free radical. Okay, and you've heard this term probably like, skin creams, those kinds of things will scavenge, they'll go after free radicals in the skin or whatever. Free radicals just mean that they have at least one unpaired electron. Okay, so that is a radical, and that makes them very, very reactive. Okay, so they're looking to react with water, so any moisture, oxygen, whatever it can, to pair up that lone electron with something else. Okay. And so these are things that, will do damage to skin cells, for instance. And so the skin creams that we put on to prevent that will preferentially react with these radicals so that it will leave the skin cells alone. Okay. All right. And in the chemistry of the upper atmosphere, like why there's an ozone hole, it's all about these really reactive free radicals, different kinds of radicals. Okay, so the only other one I want to go through today is NO2. Okay, so again, another exception because this will give an odd number again. And so if we look at this, so we've got 6 times 2 for the oxygens, and then another 5 for nitrogen. So now we've got 17 valence electrons. So let's draw a possibility here. Okay, so that's 4, 5, 6, 7, 8, 9, 10, 14, 15, 16, 17, we'll say. Okay. Another possibility might be this. Okay, where I move electrons from that one, we'll say. Okay, or I guess, the two possibilities for this. Okay. Or I guess, could we do this one? This is a question you have to look at. Okay. So are all these possible? Let's look at kind of the realm of possibilities. We have octets for each of the oxygens in this case. Nitrogen doesn't, but there's going to have to be an exception because an odd number. So this is, it's a possibility. Okay, these two are also possibilities. Okay, but why is this one not a possible structure, Lewis structure? And so you start to look, these oxygens are happy, they have octets. This central nitrogen, though, has more than 8. Okay, and that is never, ever going to happen. Okay, so it is possible, like we saw for NO, that nitrogen could have less than an octet. Where was that? Okay, like for instance this, right? So nitrogen had only 2, 3, 4, 5 electrons around it. Okay, but it will never ever have more than 8 electrons. Okay, so these really are the only possibilities where you've got kind of a double, single, hybrid, or just singles. Okay, and so to determine like which is better, quote unquote better, let's look at formal charges. Okay, and so this one, we've got each of the oxygens 6 minus 1 minus 6, so there'll be a -1 charge. And then the central nitrogen is going to have 5 minus 2 minus 1, so that's a +2. Okay, so probably not the best. Okay, and so if you look at these in comparison, each of these oxygens, or this one, the double bonded oxygen, is going to have 6 minus 2 and then another 4, so that'll be a 0 charge. This oxygen is going to have a 6 minus 1 minus 6, so it's going to be a -1. And then this nitrogen is going to be 5 minus 1, 2, 3, 4, so that's a +1. Okay, and so now you only have formal charges of plus or -1, and then the final check is the minus charge on the most electronegative atom? And it is, right? So it's on the oxygen. Okay, and then likewise here, you could say minus, plus, and 0. Okay, so the negative charge is on the most electronegative atoms, so that is also good. Okay, so the best Lewis structure for nitrogen dioxide is a resonance form. Okay, so this one and this one. And I'm drawing it purposely here as bent, okay, because it's going to be a segue for what we are going to talk about next week of the shapes of molecules. Okay, so whenever you have at least one electron here, you start to repel these electrons, and now it goes from this, which is linear, to a bent structure. Okay, and so that's where we will pick up next week. So enjoy your weekend.